Bayesian estimation, estimating the parameter of distribution. 14.2.1 Discrete variables. Let us say that each instance is a multinomial variable taking one of k distinct states. Section 4.2.2. We say that xi to the t equals to 1 if instance t is in state I and xj to the t is equals to 0 for all j not equals to I. So the parameters are the probabilities of states q equals to the transpose of the vector q1, q2, q3 until qk with qi starting from 1 to k, satisfying qi greater than or equals to 0 for all I and the sigma qi summing for all I equals to 1. The sample likelihood is p of x conditioning on q is equals to a double multiplication pi of t starting from 1 to n and also pi of I starting from 1 to k of the term qi to the xi to the t. So the prior distribution we use is the Dirichlet distribution. Dirichlet of q conditioning on alpha equals to tau of alpha 0 divided by tau of alpha 1 times tau of alpha 2 and so on times tau of alpha k of the term pi the multiplications of I starting from 1 to k of the qi to the alpha I minus 1. So where this alpha is the vector of the transpose of alpha 1, alpha 2, alpha 3 until alpha k, and the alpha 0 equals to sigma alpha I summing for index I, alpha I being the parameters of the prior are called hyperparameters. Tau of x is the gamma function defined as tau of x equals to the integration of u to the x minus 1 times e to the minus u du, integrating u starting from 0 to infinity. For example, x to the t may correspond to news, documents, and states may correspond to k different news categories, sports, politics, arts, and so on. The probabilities qi then correspond to the proportions of different news categories, and priors on them allow us to code our prior beliefs in these proportions. For example, we may expect to have more news related to sports than news related to arts. So given the prior and the likelihood, we can derive the posterior p of q conditional on x, which is proportionally to p of x conditioning on q times p of q conditioning on alpha. And such combinations of the multiplication of probability is also proportional to pi, where pi is for multiplication for all index I of the term qi to the alpha I plus ni minus 1, where ni is the sigma of xi to the t, summing for all t starting from 1 to n. We see that the posterior has the same form as the prior, and we call such a prior a conjugate prior. Both the prior and the likelihood have the form of product of powers of qi, and we combine them to make up the posterior. P of q conditioning on x equals to tau of alpha 0 plus n divided by tau of alpha 1 plus n1 times tau of alpha 2 plus n2 and so on until times tau of alpha k plus nk. And after we do the divisions of all taus and the multiplication in the denominator, we apply the pi multiplying for all index starting from 1 to k of qi to the alpha I plus ni minus 1, and which by definition happens to be the Dirichlet of q conditioning on alpha plus n, where n is the transpose of the vector n1, n2, n3 until nk, and the sigma ni summing for index I is equals to n. Looking at equation 14.3, we can bring an interpretation to the hyperparameters alpha I, This is proposed by Bishop in 2006. Just as Ni are counts of occurrences of state I in a sample of n, we can view alpha I as counts of occurrences of state I in some imaginary sample of alpha 0 instances. In defining a prior, we are subjectively saying the following: in a sample of alpha 0, I would expect that alpha I of them to belong to state I. Note that larger alpha 0 implies that we have a higher confidence, a more picked distribution in our subjective proportions, saying that I expect to have 60 out of 100 occurrences belong to state 1 has higher confidence than saying that I expect to have 6 out of 10. The posterior then is another Dirichlet that sums up the counts of the occurrences of states imagined and actual given by the prior and the likelihood respectively. The conjugacy has a nice implication. In a sequential setting where we receive a sequence of instances because the posterior and the prior have the same form, the current posterior accumulates information from all past instances and becomes the prior for the next instance. When the variable is binary, x to t is chosen among the sets 0 and 1 by either one of the values, and the multinomial sample becomes Bernoulli. That is, p of x conditional q equals to pi multiplying for ot of the term q to the x to the t times 1 minus q to the 1 minus x to the t, and the Dirichlet prior reduces to the beta distribution. Beta of q conditioning alpha beta is equals to tau of alpha plus beta divided by tau of alpha times tau of beta, and such a ratio times term q to the alpha minus 1, then times 1 minus q to the beta minus 1. For example, x to the t may be 0 or 1 depending on whether email with index t in a random sample of size n is legitimate or spam, respectively. Then defining a prior on q allows us to define a prior belief on the spam probability. I would expect, on the average, alpha divided by alpha plus beta of my emails to be spam. Beta is a conjugative prior, and for the posterior we get p of q conditioning on a and alpha beta is proportional to the following value: q to the a plus alpha minus 1 times 1 minus p to the n minus a plus beta minus 1, where a is sigma of x to the t summing for all t, and we see again that we combine the occurrences in the imaginary and the actual samples. Note that when alpha equals to beta equals to 1, we have a uniform prior, and the posterior has the same shape as the likelihood. As the two counts, whether alpha and a beta for the prior or alpha plus a and the beta plus n minus a for the posterior increase and their difference increases, we get a distribution that is more picked with a smaller variance. See figure 14.2. As we see more data, imagined or actual, the variance decreases. Continuous variables. We now consider the case where instances are Gaussian distributed. That is, p of x is approximated by the normal distribution of with parameter mu and the sigma square, and the parameters are mu and sigma square. We have already discussed this briefly section 4.4. The sample likelihood is p of x conditioning on mu and sigma square equals to multiplications multiplying for ot of 1 divided by the square of 2 pi times sigma, then times the exponential of the term minus times x to the t minus mu to the t to the square, then divided by 2 times sigma squared. So figure 14.2 is the plots of beta distributions for different sets of alpha and beta. There are 4 sets: beta 1, 1, which is just a line, beta 2, 3, beta 4, 6, and beta 20, 30. The larger the value, the steep the shapes. Now the conjugate prior for sigma is Gaussian, p of mu, which is approximated by the normal distribution of mu 0 to the square, sigma 0 to the square, and we write the posterior as p of mu conditional fancy x equals to, which is approximated by the value of p of mu times p of fancy x conditional mu, which is approximated by the normal distribution or the Gaussian distribution of mu n and sigma n to the square, where the parameter mu n is equals to sigma squared divided by n times sigma 0 squared plus sigma squared, then times mu 0 plus n times sigma 0 squared divided by n times sigma 0 squared plus sigma squared times m, and 1 divided by sigma n squared is equals to 1 divided by sigma 0 squared plus n divided by sigma squared, where m is equals to the sigma summing for all x to the t divided by n summing for all t is the sample average. We see that the mean of the posterior density, which is the Bayesian estimate, mu n, is a weighted average of the prior mean mu 0 and the sample mean m, with weights being inversely proportional to their variances. See figure 14.3 for an example. Note that because both coefficients are between 0 and 1 and sum to 1, mu n is always between mu 0 and m. When the sample size n, or the variance of the prior sigma 0 to the square is large, the Bayer's estimator is close to m, relying more on the information provided by the sample. When sigma 0 to the square is small, that is, when we have little prior uncertainty regarding the correct value of mu, or when we have a small sample, our prior guesses mu 0 has higher effect. Now sigma n gets smaller when either of sigma 0 or sigma gets smaller, or if n is larger. Note also that sigma n is smaller than both sigma 0 and sigma divided by the square of n, that is, the posterior variance is smaller than both prior variance and that of m, incorporating both results in a better posterior estimate than using any of the prior or sample alone. Now, figure 14.3, 20 data points are drawn from p of x, which is approximated by n of 6, 1.5 to the square. Prior is p of mu, which is approximated by n of 4, 0.8 to the square. And the posterior is then p of mu conditional x, which is approximated by n of 5.7, 0.3 to the square. Now, variance is smaller than both prior variance and that of m. Incorporating both results is in a better posterior estimate than using any of the prior or sample alone. For the case of variance, we work with the precision, the reciprocal of the variance, that is lambda, divided by 1 divided by sigma squared. Using this, the sample likelihood is written as p of x conditioning on lambda, which is equals to pi of t of the term lambda to the square root of lambda divided by the square root of 2 pi, then times the exponential of minus lambda divided by 2 times x to the t minus mu to the square, which is, if we take out the constant, which is unnecessary within the pi multiplications of the exponential function, that will be lambda to the n divided by 2 times 2 pi to the minus n divided by 2, then times the exponential of minus lambda over 2 times sigma of x to the t minus mu to the square, where the sigma is taken among all possible t, because we take away the pi, so that the exponential of lambda has n increases, and also the exponential of 2 pi also has n increases. And also, since we take out the multiplication, the term inside of the exponential function should be summing together. So the conjugate prior for the precision is the gamma distribution p of lambda, which is approximated by gamma of a0, b0, which is equals to 1 divided by tau of a0, then times b0 to the a0, then times lambda to the a0 minus 1, then times exponential of minus b0 times lambda. And the posterior is p of lambda conditioning on x, which is approximated by p of x conditioning on lambda times p of lambda, which is approximated by gamma of an bn, where an is equals to a0 plus n over 2, and bn is equals to b0 plus n over 2 times s squared, where s squared is equals to sigma of x to the t minus mu to the square divided by n, and the sigma is taken among all possible t, and such kind of value s squared is the sample variance. Again, we see that posterior estimates are weighted sum of priors and sample statistics.